Okay, this is the paper we are discussing today. A2, paper number 2, right? Okay, 2024, Unit 6 paper. Answer the questions, right? Compounds P and Q are crystalline solids. P is a white and contains one cation and one anion. A white it contains one cation and one anion. It's white color. Q is a pale violet, contains two cations and one anions. Pale violet color. Uh, Both are solids. Right? Pale violet means purple color, right? Something purple. Student carried out tests to identify P and Q. Complete the table to show by name or formula the products of the test. Tests. Aqueous silver nitrate and dilute nitric acid were added to a sample of an aqueous solution P. Silver nitrate they adding, right? Concentrated ammonia. So they're adding copy white color. Right. One cation and anion is there. Then concentrated solution was added there. So same thing that we have discussed in AS, right? So there it must be a halide. A yellow color precipitate was formed. So we can assume, right, that the anion is what? Since we are getting silver iodide, we can assume the in P the one of the anions. There's only a cation and anion. We can assume it to be I minus. So they are asking the precipitate, right? Not the anion. So it must be silver iodide, not the precipitate. Silver iodide with the state. Um, Sample of solid Q, right? It has two cations and one anions. Was added to 5 cubic centimeters of aqueous sodium hydroxide, and the mixture was warmed, right? So, okay. A pungent gas was evolved, which turned damp litmus into paper blue color. So, red color litmus paper into blue color means we can imagine the gas must be red into blue color means the glass should be alkaline gas. So, only alkaline gas we are studying, right? Is what ammonia. So, it must be something ammonia gas. Something must be related to ammonia, or if the ammonia gas is released, we can assume they say it contains two cations and one anion. So ammonia gas to release ammonia gas, if you have ammonium NH4 plus cation in the presence of since ammonium, right, is slightly acidic, in the presence of ammonium cation, when you put a sodium hydroxide, when you put a strong base, it is releasing ammonia gas. So now we know, we can assume one of these cations could be ammonium, right? Uh, the red brown precipitate was paper blue. Red brown precipitate was formed, which was insoluble in excess alkaline, right? So they are adding sodium hydroxide now. So right. So there must be cation forming brown color precipitate, which was formed, which was insoluble in excess alkaline. A brown color precipitate, we can assume something iron, right? Maybe Fe3 plus. Can't tell it for sure, but you can assume like if we had the Fe 3 plus, right? FeOH thrice. So it is kind of like a white is brown color. We don't know. We can just assume, right? A gas force, they are asking about a gas, so you can tell ammonia. The precipitate force, so let's say if we had the Fe, Fe1 is Fe3 plus, other one is ammonium. You can just assume the cations could be these two. So if we had Fe3 plus, the cation we can assume it to be, we can't tell it for 100% accuracy. It has a little bit of doubt, right? FeOH rice, a brown color precipitate. Just assumptions. Maybe we are wrong, right? Aqueous barium chloride and dilute hydrochloric acid were added to sample of solution Q again because now we can assume we identified two cations. There's another anion. A white color precipitate was formed. Um, barium chloride is added and hydrochloric acid is added. Uh, white color precipitate was formed in the presence of barium chloride. So the other one is anion. Anion is unknown. So you know when barium is added, usually bread and butter, barium is added to identify sulfates. So barium sulfate is a white color precipitate, right? So these are repeated questions in the paper. Usually in the paper they are asking these questions, right? Uh, halide for halide, right? Halide question, silver halides, silver chloride, silver iodide. These are bread and butter stuff. Even A's and A2s, right? So white color precipitate in the presence of barium chloride, barium sulfate, right? Everyone knows about it. So we can assume it must be just an assumption. Maybe you are wrong. Barium sulfate, I am teaching you how to think in an exam situation. Barium sulfate precipitate. So just assume it is barium sulfate. And with the knowledge we have, right? Um, okay. White color precipitate is formed. Yeah, this is the only option we can give with our knowledge, right? So let's with confidence, let's move. Yes, right. Uh, yes, right, right. Okay, these are very easy questions, right? A green flame was seen when the flame test was carried out on a sample of P. Identify P by the name of formula. P. Uh, P is white color, cation and one anion. Right? We identify one anion, cation we don't know. To identify cations, we are doing the flame test. So this thing you should identify, memorize. Green color flame, usually, right? So now when it comes to green color flame, right, is given of what? Right? Barium. So that thing you must memorize, right? For barium and for copper color, flame test, it gives a green color, but for copper, we usually call it as one apple green. It's a specific green color. So it must be barium. So they are asking about P, not the ion. Remember careful. So we identified it as I minus anion, cation. It is so barium what? Barium iodide. Without an issue, you can score marks here, right? Without putting any effort. Uh, Moving on to next one. Give the formula of three ions present in Q and hence the formula of compound Q. Right. Um, the formula of the three ions. Right. So we have identified Q, hence the formula. So three ions in Q. So we identified sulfates are there. SO4 2 minus. And cation we identified there as ammonium plus. From there we released ammonia gas. And what's the other one? Other one is Fe3 plus, ferric ions. So now they are asking about the formula. So you remember cations are right to the right hand side, anions, cations are the left hand side, and uh, here between these two, Fe3 plus the metal cations. Later you will learn now metal cations are forming complexes, right? So we usually by the convention, since the metal ions is written first, metal cation, then if there's another cation like ammonium, you write it later. We still haven't decided how many of these are there. Another one is sulfates. Right? Remember Fe3 plus SO4 2 minus, right? And remember both are plus and plus, they are therefore it must be plus 4. To counterbalance this charge, you must have what? Two of these. FeNH4 twice. Right? You have to come up with this. Right? FeNH4 twice. Then only you are getting a neutral. So they are asking about the compound. When they ask about a compound, this compound must be neutral. Not an ion. They are not asking about ion. Right? There are complexes with having a charge. So it's an ion. But here they are talking about the compound. This compound must be neutral to have the charges cancelled off, to balance the negative charges and positive charges. This is the only possible answer, right? Best answer is this. I am not saying there can be other answers, but this is the best possible answer, right? Because scientists are also deciding on the compound based on what the best possible answer. They haven't seen these compounds, right? In chemistry, all based on assumptions. Best possible answer you just give. That is why in the test also we are making assumptions. We are scientists. We can only make predictions. At 100% accuracy we can't tell. We need more tests. Even still we can tell only to a certain percentage. So we are writing best possible answers. Therefore, there still can be some doubt in your head. That's normal. Right? For in 100% we can't show off our answers, right? In chemistry, especially practical tests, identifications, right? That's the nature in chemistry. A student added a sample of pale brown aqueous solution Q to a colorless aqueous solution B. Pale brown aqueous solution. Here they said precipitate was formed, which was insoluble and alkalized. Red brown precipitate. They are talking about red brown. Now they said a pale brown aqueous solution of Q. Okay, now you have Fe, you have ammonium, and also you have sulfate. Q to a colorless solution of P. Now you have to be very, very careful. You have to think of the ions, right? There are three ions versus two ions. Now we in P we have barium 2 plus, right? P means we knew barium iodide. Barium iodide and ammonium sulfate are getting mixed. So you know it can form barium sulfate, right? You must identify it. The answer itself was also given there. You can have a barium sulfate precipitate because sulfate ions are there. There's a possibility having a white color precipitate. Um, yeah. So that is for now. That is my observation for now, right? Formation of a darker brown solution along with white color precipitate. Right, white color precipitate is observed. Brown color solution. Right. You have Fe3 plus anyways. Darker brown solution. Explain why the student, right? The student concluded from the formation of a darker brown solution that The redox reaction had taken place. Right, redox reaction means you had I minus, right? And also Fe323 plus. We are just making assumptions. We are trying to tell a perfect lie, right? So they have given one of the hints, redox reactions also, right? I am also just like you writing a paper, right? Otherwise, I could have just look at something else and tell you answers. No, I minus. A redox reaction. So when they are talking about brown color means I2, right? I2 must have been formed. I2, aqueous is brown color. Another one is what? I minus must have got oxidized and Fe3 plus. The only other one is must be Fe3 plus into Fe2 plus. That is my judgment. Maybe I am wrong. I minus into I2. So this is what is giving the what? A darker brown color I2. Very interesting questions. Darker brown color. Right. Okay. So you can explain it. 2 points. They are not asking about. So you can write the balanced equation which you like. Right. They don't expect it. Now if you write it even, it is very right. Not much of effort. Right. Two electrons are moving. Um, and for that you need two of these. Now it is balanced. Charges are balanced. Right. Four. Yes, four charges are balanced. Right. Until I minus is getting oxidized, Fe3 mass is getting reduced. Presence of I2 in aqueous medium gives the darker brown color observations. Very easy stuff. Aqueous, actually I2 is not getting soluble. Usually I2 with the presence of I minus, it is becoming I3 minus. Right? Actually it is I3 minus. To have I3 minus, you have to have what? Another I minus. So actually it must be practically I3 minus. You don't need to know up to that level, right? Okay, I3 minus. Because I2 is not getting dissolved. In the medium, it is making a little anion. I2 is making an anion with I minus and gives I3 minus anion. This is soluble. I2 is not soluble. Why? It does not have charge. So it is very less polar. Water is polar. So non-polar molecule with a polar medium. That is why solubility is very weak. But I3 minus is a polar molecule. In a polar medium water, it is getting dissolved nicely. Right? Question number 2. A group of students investigated the kinetics of a reduction of peroxide disulfate ions by iodide ions in the aqueous solution as shown in reaction 1. Interesting one. I minus into I2, thiosulfate into sulfates. Bread and butter questions, right? Iodometric titrations are always being asked, right? Some of the iodine produced in reaction 1 may be removed by including the portion of sodium thiosulfate in the reaction mixture. Right. So they are making an assumption. Some of the iodine, this iodine is getting removed with thiosulfate. So basically thiosulfate is reacting with I2. I2 is getting reacted with this is thiosulfate, right? H2O3 is thiosulfate. This is not the thiosulfate, right? This is peroxide disulfate. This is thiosulfate. So peroxide disulfate is reacting with I minus and gives sulfates. And that released iodine is again it's a back titration. Released iodine is again reacting with thiosulfate and giving H4O6. Right? So with the in the first reaction you are releasing I2. That I2 is participating with the second reaction. If the first reaction is not happening, second reaction is not happening too, right? So the moment the first reaction stops, after a few minutes, second reaction is also stops. Why? Uh, Second reaction. Okay, second reaction is giving I minus again. That I minus is again releasing I2. It's a chain reaction. This I minus is released. This I minus is again participating in the first one, right? So until S2O8 2 minus is over, this reaction 1 and reaction 2 is happening until S2O3 is over. Or uh, the total reaction will stop from the first reaction if S2O3 is becomes over, right? So it depends. If the S2O8 is the limiting reagent, the moment S2O8 is over, reaction will stop. The chain will stop. If S2O3 2 minus is the limiting reagent, then the moment the concentration of this comes to an end, the reaction will stop, right? After all the thiosulfate ions have reacted, the further iodine produced can be detected. So it means thiosulfate is the limiting reagent. You do the first reaction, I2 is made. That I2 is getting reacted again with thiosulfate and producing I minus, and again gives participating in the first reaction, right? So until thiosulfate is over, continuously first and second reactions are happening. The moment thiosulfate is over, I minus is becoming the limiting reagent here. Right? So until I minus is becoming over, reaction is happening. Right? Okay. So usually they are doing this in kinetics to delay the reaction. Right? Why? Uh, First reaction is happening faster. So you are measuring the rate of reaction by observing the presence of I2. Right? Because I2 can be detected with what? Starch. Right? Starch iron complex. Right? Starch iron complex is blue color. But this reaction is very fast. The moment you put I minus and S2O8 2 minus, reaction is happening so fast. Instantly you are getting a black color, so you don't have time to on and off the stopwatch. This reaction is very fast. So you have to delay the reaction. So what you do is all the I2 made is getting converted into I minus again. So therefore now a delay. The black color comes later. Why? The first reactions happens and the second reaction is converting I2 into I minus. So therefore, blue color does not appear. Why? All the I2 is again reconverted back into I minus. This happens until thiosulfate is there. So until thiosulfate is over, you are not seeing black color. Right? So there's a delay in the reaction. You do it because the first reaction is very fast. Right? And we can assume second reaction, first reaction is faster, second reaction is a slow reaction. Right? Okay. So until the second reaction is over, we can't observe anything. You will not see a black color, the blue color formation, right? So thanks. So that is why this experiment is designed this way. This procedure is designed this way, right? For us to discuss about this is easy, but remember, scientists have spent a lot of years developing these methods, right? Okay. Anyways. Now you do the first one and the second one. So remember, all these things are in the same reaction mixture, one reaction mixture, right? This is reacting with I minus and I2 is made. I2 is getting converted into I minus again. That I minus is again getting converted into I2. But remember, I2 will not be there in the mixture until thiosulfate is over, right? Okay, so therefore you have enough time to on and off the stopwatch. Otherwise, first reaction is happening so fast. Right? Volumes of the solution used in the mixture are shown in the table 1. They have given kinetics. Now, if I tell you again, the purpose of doing this experiment is finally what? With this experiment, you can find the order, reaction order. With the reaction order, we can reduce the mechanisms, right? That is the purpose. We are doing this experiment to find the order of the rate equation with respect to each reactant. If you know the order, you can come up with the rate equation and also and the order of the rate equation for respective reactants. If you know the order, you can deduce a mechanism. So at the end of the day, the purpose of doing this experiment is to decide on the mechanisms. Mechanisms are how atoms or molecules are connected to each other, how the reactions are happening. Remember, we can't observe these things. We can't see atoms and electrons are moving here and there. So those are only estimations, predictions, right? So we can only make accurate predictions, more successful prediction based on this experimental data. With bit of mathematics, we can deduce on the mechanisms. Right? Otherwise, how can know with arrows atoms and molecules are what? The bonds are being broken, bonds are being formed. So all those things are decided based on the experimental observations we have made, and mathematically we have found a way to deduce the mechanisms. So at the end of the day, deducing reaction mechanism is the purpose of doing these rate equations or rate experiments, right? So without knowing the mechanisms, we can't synthesize new molecules. Keep that in mind. As organic chemist, we have to make synthesize new molecules. We cannot synthesize new molecule if we do not know the mechanisms, right? But there's nowhere to know the mechanism because we can't see atoms and molecules. So therefore, we have found a mathematical, a logical approach. We do an experiment, rate equation, and do rate experiment. With that, we have find the order of the reaction rate equation. With that order, we can come up with the mechanism. If you know the mechanism of the reaction, we can use that knowledge to synthesize new molecules. Right? It's a very long procedure, right? It takes about to synthesize a new molecule. It takes a lot of time, years. Right? Some scientists have got the Nobel prizes for reducing the mechanisms, biochemical pathways happening in the bodies. Right? For reducing, for example, Grignard. Right? There's a mechanism called Grignard mechanism. He got the Nobel Prize for it. Right? Lord, most of the some of the Nobel prizes for biology and medicines and chemistry, they are winning these Nobel prizes for understanding these mechanisms. So you can understand why learning these basics are very vital. This is where some you can tell where organic chemistry is connecting with physical chemistry. Right? There are branches in chemistry called organic physical chemistry. Right? Anyways, concentrations are given potassium iodide, potassium peroxide sulfate is given, sodium thiosulfate is also given concentrations. So when you look at the concentration, you can see potassium iodide high concentration is given, potassium peroxide sulfate compared to thiosulfate is a higher concentration. So therefore, you know thiosulfate is low concentration. That is why it becomes a limiting reagent, right? Otherwise, before thiosulfate ends, the potassium peroxide sulfate will come become more. So you have to make sure the concentration of sodium thiosulfate is lower, must be limited. Right? Uh, A few drops of starch solution are added to 5 cubic centimeters of sodium sulfate in a solution in a small beaker, right? Potassium peroxide disulfate solution and water added to the beaker. So all are in the same reaction mixture. The potassium iodide solution is also added. The mixture stirred and timer is started. Ah. Now, if we haven't had the second reaction, you will not have enough time to switch on the timer. The moment you put them together, it will turn into blue color. That reaction is very fast. First reaction is a very fast reaction. Keep that in mind. Right? Okay. Time taken to change the color is recorded. The procedure is repeated for each mixture using the volume shown in the table 1. Right? So they have taken what? Same volume of H2O3, volume of potassium iodide. So they are trying to find uh, how the rate is changing when the I minus concentration is changed. Right? So that is what they are trying to find. These are practicals actually we do in the Cambridge. Right? So Edexcel people are not doing these because they are not having a practical paper, not alternative one. Rate is proportional to I minus n. We don't know the order. And H2O3 concentration, we are taking a high concentration. When the high concentration is there, irrespective of the order of H2O8, right? Since the concentration is very high, we can assume relative to I minus, this concentration is much larger, right? H2O8 concentration, right? Uh, and the volume also larger, right? Let's see, the concentration is given. No, it has a higher concentration here, H2O3. Um, this concentration is given, and so therefore that concentration is maintained. So we can assume the concentration is not getting changed. So we can make it a constant here. Right? Why we can assume the concentration of H2O3 is not getting changed, right? Because we are measuring the initial rate. Keep that in mind. Why the concentration of H2O3 is not getting changed? Total volume is made constant, right? See, volume of this is 20, and they make sure total volume is constant. So therefore, K2 of H2O8 concentration is remaining constant, right? So therefore, rate is proportional to, since H2O8 concentration is remaining constant, rate is proportional to I minus concentration into power of n. Right? So they have changed the concentrations, and so you can assume it as what? Uh, uh, this is actually comes under what? Initial rate method. Initial rate method. So we assume the rate is right. So actually we are finding the average rate, right? So we are assuming the average rate and the initial rate both are the same. It is not actually like that. Why? If you look at the rate, if the order is not um, zero order I minus, then the rate must go down. So we can assume, right? Even though rate is going down with the decrease of concentration of I minus, since the reaction is happening faster, if it is, yeah, since we are taking the average rate, right? If the slope is not that steeper, If it is happening very slowly, you will have a very steep curve. So therefore, finding you are assuming the initial rate and the average rate is the same, the prediction is wrong, right? But here, since the reaction is happening faster, right? It is the curve is not that steeper. So therefore, even though we are measuring the average rate, we can assume the average rate and the initial rate both are the same, right? Because you are getting a kind of like a line, straight line, not a straight line. There's a curvature, but since the reaction is happening faster, making this assumption is okay. Considering the we are calculating here the average rate, right? How long it takes to uh, yeah, yeah, we are taking the average rate, right? So making that assumption is fine, right? Average rate and the initial rate is the same. That assumption is to a certain extent it is okay. Right? You don't need to know to at level. Right? Anyways, we are here observing how long it takes to bring the blue color complex. Right? The moment you start in the blue color complex, we stop the reaction. When we are doing the practical, actually, we have the flask on the white color plate, and we make a cross, right? So therefore, we actually check how long it takes to disappear the cross, right? Otherwise, there will be a issue with the color intensity, right? Because blue color in one experiment, when light blue is there, you are stopping the reaction. In another reaction, when the dark blue is there, you are stopping the reaction, and it has an error there. But in both the occasion, if you make a cross, the moment the cross disappears, you are stopping the reaction. Then it makes the experiments even, right? Okay. So they are keeping the uh, they make sure that they are making sure that K2S2O8 concentration constant and I minus concentrations are initial concentrations are changed, right? And they are with this experiment we are finding the initial rate. We are calling this an initial rate method, right? Initial rate method. There's another method called instantaneous rates. So in that case, we have to take a portion out, right? In the instantaneous rate method, we'll have to take a portions out and find the concentrations of each portion, right? And along with time, we find the rate of each point, right? But this is the instantaneous rate method. This experiment is easier, but this experiment can only be done for faster reactions. Slow reactions, you will have to use the not the initial rate method, instantaneous rate method. So you will have to take a portion from the solution and find the concentration with the titration, and you have to stop the reaction from happening in each portion you are taking. It's kind of like a complicated method, right? This one is easy. uh, right. Suggest a suitable piece of apparatus for measuring the volume of the potassium iodide solution, right? Now remember the first reaction, when the color appears, the the concentration of I minus is not coming into zero, right? Keep that in mind. Okay. The moment blue color appears, we are stopping the reaction. So by the time blue color appears, the concentration of I minus is not zero, right? It may only change a little bit, right? So that is why we are assuming when the blue color is formed, even though I minus concentration has gone down a bit, we assume the initial concentration of I minus is staying the same, right? Otherwise, without that assumption, we can't do this experiment. Suggest a suitable piece of apparatus for measuring the volume of the potassium iodide solution. Right? Uh, Potassium iodide. So these are volumes. So you can't use a pipette. Yeah, the fixed volume pipette is there. The variable volumes are there, but the best one is the burette, right? But when you look at the number of significant figures, decibel places, it may seem like they have not used the burette, because if they are using the burette, they are writing the values up to 2 decibel place, right? But they have done only 1 decibel place, right? So the best answer would be graduated pipette. And there are two pipettes, fixed volume pipette and the graduated pipette. Graduated pipette is the one that you can make variable volumes. By looking at the data, you can tell they have used the graduated pipette, right? Because with the burette, you can write the answers into another significant figure, but uh, you if you write only pipette, your answer is wrong. Because there are two types of pipettes, fixed volume and the graduated. So you must mention it as graduated pipette. For burette also they will give you marks, but I don't like that answer because if they have used burettes, they could have given the values up to 2 decibel places. So the answer is graduated pipette or burette. State the final color. State the final color of the reaction mixture in step 3. What is the final color? Blue black color. Right? Blue black color is the final color. Blue black color. The reciprocal of the time taken for the mixture to change color can be used as an approximate measure of the initial rate. Right? Actually, rate is proportional to what? Rate is difference in what? Rate is equal to delta minus delta reactance. I am calling as minus delta because concentration change is negative. Why? Final weight difference is negative. Why? The weight is decreasing, so the weight difference is negative. So if we write the difference as it is, the rate becomes negative, right? Why? In the reactors, concentration is decreasing. So therefore, the delta R value will be, the difference will be negative. To make the delta value positive, otherwise the rate is becoming negative. Rate cannot be negative. So therefore, it must be, if we are writing the rate using the reactant concentration, change the reactant constant, it must be negative. Negative is delta T. Or the product concentration is going up, delta product into delta T. Right? So in that case, it is positive because product concentration going up now. Um, the question is, right? It is 1 over T. Why 1 over T can be used? Why? We can assume the amount of products formed is all the time same. Right? Why? The blue color appears when a certain amount of product is formed. Right? So delta P value is always constant. Why? The blue color appears when the same concentration of product is formed. So therefore, we can write it as rate equals delta P is always constant. Therefore, you can call it as what? K over delta T. Right? So therefore, we can remove equal and K. So rate is what? inversely proportional to delta t. Right? This observation is this this is reasonable. Why? Because of the setup. As per the setup, when the observation is made all the time, the amount of products or the amount of reactor that has been reduced, or the amount of reactors that has been reduced, or the amount of products that has been increased is always constant. So therefore, you can make the assumption as rate is initially proportional to T because T is the only variable, right? Because product or reactant change in product or reactant concentration is always constant. I hope it is clear because the measurement is made all the time when the same number of same concentration of product is there in the solution mixture, right? That is why we can make this assumption. State why the amount of added thiosulfate ion should be much smaller than the amount of peroxythiosulfate iodide ions for this approximation to be valid. Thiosulfate is low. Why? We have discussed it, right? If we add greater amount of this, what will happen? You know it is going in cycles now. First reaction is happening, this is again coming here and it is getting moved back to here. Right now, if we had a greater number of moles of thiosulfate than this, what will happen? Before thiosulfate is becoming coming to an end, this will comes to an end, right? So then what you can measure the rate. Why? There won't be a blue color formed. Why? H2O3 is becoming over, right? Then in the medium, what will have, you will have only I minus. Why? I minus is not getting converted back into I2. Why? The thiosulfate, the H2O8 is over now. And you have H2O3 in excess compared to H2O8. So therefore, all the I2 that has been converted by H2O3 will be converted by I minus, and that I minus is not getting converted back into I2. Why? Before running out of H2O3 2 minus, H2O8 2 minus has come to an end because you have a larger number of H2O3. So this will not come to an end. This will come to an end. I'm talking about number of moles, right? So you will not be able to see an observation. So you must write it in your own words, right? Otherwise, you will run out of what? H2O8 and there will not be enough H2O8 to have I2 in the medium. Uh, A2, A3, right, right. Uh, the results that student M obtained are shown. Complete the table with iodine ion concentration mixture. So they have given it. Just have to uh, I minus concentration is in the mixture number 3 is over, but rate is given, uh, time is given, right? So you must find the iodine concentration using the information in the table, right? So have they given us the rate equation? Yes, they have not given the rate equation. Yeah, not rate equation is not given. We don't know the order, right? Um, volumes are given here. I minus volume is I minus volume is given. Okay, so they are telling about the initial concentration of I minus. So they are given us the volume. So you must multiply this with the dilution factor, right? So the volume is 11. Concentration is also given there. That's the concentration. They have mentioned the concentration as that's concentration. Ah, point 2, right? Point 2, volume is 11. Point 2 is there in 1000. This is my way of doing it. In 1000 you have point 2 and they have used 11. Then this number of moles are there in the solution. Right? This number of moles. This is the number of moles in the solution. Point 2 in 1000, then 11. Now this number of moles are in total solution of what? They are making sure the total volume is what? 20, 18 plus 2, 20. Then 40, 45. Am I okay? Yes. Total volume is 45, right? 20, 25, 45.
Yeah, the 45.
45, right? So therefore, this number of moles are there in 45 of volume. Then in 1000. This number of moles are there in 45, then in 1000. Right? So now you can sort it out in many ways. This is my way of doing. So actually it's easy, right? 1000 to 1000 getting cancelled off. Finally, point 2, 11.0 divided by 45. What did you get as the value?
So I got 0.049 and also definitely
0.049.
49.
Yes.
Yes, yes.
0.049.
So I basically divided 11.0 by 45.0 into 0.809 for definitely.
Okay, good. Right. 0.04. See? So you have to be careful of the significant figures. Yeah, you can point to the concentration is given it as point 0.2, right? So there's only one significant figure. So let's see. Here. Three significant figures are there. Yes. Then fine, no issue. Right? Three are there. So right, yes. So 0.049. Plot a graph 1 over time against the iodine concentration. Right. So if you have sketched it, so 1 over time is rate. So it is actually rate versus 1 over time is rate with the I minus concentration. Right. As per the given data, rate is what? It is a straight line going to the origin. Right. So straight line means the order must be one. Right. Rate is uh, yeah. The order must be one. Yeah, that is why you are getting a straight line, right? By looking at the graph, you can decide on the order. So they must be asking that what is the order. Remember, when you are sketching the graph, at least 50% of both the axes must be covered. It must go through the origin because the data is given that way usually. So make sure if the graph is meant to go to the origin, always draw your graph through the origin. But when you are doing an experiment, don't be like that. It is like you are manipulating your research, but you don't do the practical. No, they are the ones who are giving us the data. No, so they are with their data. Usually, you might the graph if it is meant to go through the origin, it must go through the origin. So this is meant to go through the origin. So always sketch it this way, right? Okay. So always label the axis. So those are little things, units and all. Pick a scale. Again telling you, at least 50% must be covered. Uh, right. Reduce the order. What is the order then? First order by looking at the graph. Yes. Straight line. Justify your answer. Since the graph is the straight line going through the origin, with respect to rate, I minus concentration is unknown. Since it's a straight line, you can tell the order is 1. Student N carried a sequence of experiments to find the order of
So
reaction.
can you explain again about finding the order, please?
Okay. So this experiment is carried out, right, to find the order. So remember, now rate is equal to I minus n. N is the order. Now if n is 0, right, n is 0, let's say it is 0, rate is equal to what? Let's remove this mark, what? Equal k. If n is 0, any value into power of 0 is what? 0. K into 0. So therefore rate value is what? Okay, into 0 is 1, right? Into power of 0 must be 1. I minus into power of 0 is 1. Right? 10 to the power of 0 is 1. 20 to the power of 0 is 1. So therefore I minus into power of 0 is 1. So therefore if the order is 0, rate is constant irrespective of the concentration of I minus. Right? Then you will get a straight line. If the order is 0, is it understood?
Yeah, sir.
Right. Now you haven't got a straight line like this, so therefore the order cannot be 0. Usually in your exam, the order either 0, either 1, either 2. These are the only scenarios you are getting. Keep that in mind. Either 0, either 1, either 2. If it is first order, rate is equal to K I minus concentration into 1. And what we have. So therefore it is what? If we convert this into a graph, what? Rate means y axis, K is what? Constant, M, I minus is a variable. So y equals mx type of a graph, right? Straight line. If the order is 1, it's a straight line going to the origin. So the graph we got is what? A straight line going to the origin. So therefore what? Order must be 1. In case if OD is 2, rate is equal to what? K